that means that we can transition to some basics and fundamentals in the next, basically in the remaining time. Okay, let's do this. So let's start with some fundamentals. This is an old picture of an AMD Barcelona system from 2006. And at that time, cores are actually big, but if you look at the cores, there's actually a lot of memory in them. So memory in a modern system is everywhere. Maybe that's not the best picture showing the importance of memory, but it's everywhere. Then ideal memory. It's always good to think about ideal. I like being idealistic to try to achieve that ideal somehow. Ideal memory imposes a lot of requirements. 0 latency, infinite capacity, 0 cost, infinite bandwidth. And unfortunately, we don't have that ideal because the ideal memory requirements oppose each other. Bigger is slower, faster is more expensive, and higher bandwidth is also more expensive. And we've talked about some of these. Bigger takes longer to determine the location, that's why it's slower. And faster is more expensive because faster memory technologies are more expensive. You need to pay more for them, or you need to have additional circuitry to make them fast. Like SRAM requires 6 transistors, right? Sometimes 8 transistors to make them fast. DRAM requires only 1 transistor, right? And technology is also different. That adds to the slowness part. But clearly, memory technology is a big determinant of speed. And usually faster is more expensive. And higher bandwidth is more expensive because, as we discussed, you need to add more banks, more ports, higher frequency, or some faster technology to provide you higher bandwidth. 3D stacking, for example, is fundamentally higher bandwidth, but it's going to be fundamentally more expensive also. But if you want bandwidth, you need to pay for it. So clearly, these ideal memory requirements oppose each other. And as a result, we have a trade-off, and that's why we have the memory hierarchy. Let's go through some of these technologies quickly. I guess everybody's familiar with DRAM, right? Yes? Okay. Even if not, we'll go through it quickly. Basically, this is dynamic random access memory. It stores charge in the capacitor, and the capacitor charge indicates the stored value. And whether the capacitor is charged or discharged indicates 1 or 0. This depends on your encoding, of course, right? Charged may be encoded as 1 or 0, depending on how you do the encoding. In existing systems, you can do both encodings, actually. In different parts of a chip, you can have different encodings also. We're not going to go into that level of detail. But essentially, this is little cost. You have 1 capacitor, essentially. And that's really your storage device. But to be able to access that charge or value, you need to add a lot of circuitry around it. And this circuitry is going to be relatively similar in many technologies. Essentially, you need to have an access transistor in DRAM that connects the capacitor to the bit line. Now you can sense what's in the capacitor when you enable this access transistor, right? This is called a row. Why is it called a row? Because you have a row of these cells that are connected to the same row. So you don't have a single cell. You really enable a row of cells, an entire row, as we will see in a picture. And you can read the value of the cell on the bit line. And the bit line gets perturbed a little bit whenever you connect the access transistor, such that the access transistor passes the charge over here. And there's a sense amplifier that detects the perturbation on the bit line, and that basically senses whether you have a 0 or 1 charge or no charge inside the capacitor. That's the idea. Of course, there's a lot of work that goes into building that sense amplifier, which we're not going to go into. One of the issues with this technology that we know is capacitor leaks through the RC path, the resistance conductance path over here. As a result, the DRAM cell loses charge over time, which means that it needs to be refreshed. And we're going to cover this paper that I mentioned earlier. This talks a lot about refresh, modern mechanisms for refresh, actually, which should be interesting. SRAM is another technology, which we're not going to cover as much, but a lot of the principles that we will discuss, for example, in memory computation will be agnostic to technology. Essentially, this is static random access memory. You have 2 cross-coupled inverters that store a single bit. So immediately you see that there are 4 transistors here because an inverter is 2 transistors in CMOS. There's a feedback path that enables the stored value to persist. Persist doesn't mean that it's non-volatile, but persist while it's powered on in the cell. And as I said, 4 transistors. But to be able to access this, you have 2 transistors for access. Essentially, you could get away with 1 transistor, but that complicates the sense amplifier. What normally people do is you have 2 transistors, so you can get the value over here and the value bar over here, the complement over here. And then you can do differential sensing in the bit lines. You can sense the difference, and then you can say whether you have 1 or 0. And again, this is also a row. It's a word line, basically. So you have many of these cells that are connected to the word line. Okay. Another example technology is phase change memory, which we will talk about later on, hopefully. This is the storage element over here is phase change material, and it exists in two states, amorphous or crystalline. And the amorphous state has low optical reflexivity. Crystalline state has high optical reflexivity. Essentially, that's how CD-ROMs work. They basically store it in low optical reflectivity or high optical reflectivity, and one of them encodes a 0, one of them encodes a 1. And also, amorphous state has high electrical resistivity, and crystalline state has low electrical resistivity. So you can actually shine light on it and determine your reflexivity, or you can pass current through this access device and figure out the resistance that you have over here. And this is the paper that we're going to talk about later that I mentioned early on that we wrote 10 years ago. And again, the word line is similar, although it's a bit turned around over here. Basically, this is the word line that enables access to the storage device. And this is the bit line. And then you have a sense amplifier somewhere over here. So essentially, the technologies are very similar in terms of the word line and the bit line structure and the sense amplifier. Sense amplifier is different, of course, in terms of how it senses, but as a block, it's essentially a sense amplifier. It's sensing what's inside the storage unit. So this is the reading. If you want to prefetch some of the readings, we're going to talk about that hopefully early next week. And this is a shorter version of that reading. Maybe I'll assign this as a review paper, but let's see.
So,
yes?
Basically, the phase change material is changed using the optical or the heat.
No, whenever you want to change the phase, you actually heat the material.
So the heat,
yeah, but the reading itself may be optical. Yeah. So there are two types of reading mechanism. You can do it optically, or you can do it by detecting the resistance. So the read device is different, basically, in those two cases. But whenever you want to change the phase of a material, you have a heater, essentially, and you need to heat it to very high temperatures, actually. That's one of the downsides of this technology. And we will discuss this more next week. And this paper, if you want to learn more, you can read this paper early on. This talks about the technology itself and how it works, and also describes why it's more scalable than DRAM, and it does initial experiments on what happens if you replace DRAM with this type of technology. Okay. Okay, so a fundamental concept in memory is bank. It's also called interleaving. Essentially, the problem that interleaving or banking, you don't have a single monolithic memory array structure, basically. When I say monolithic, you have a two-dimensional array of cells, right? You don't want the entire memory to be just a single monolithic array. Why? There are two reasons. One is, if you have a single monolithic array, it takes too long to access, because now your word lines become long, your bit lines become long, and your access latency becomes dominated by how fast you can activate the word line, connect the cells to the bit lines, essentially, and how fast you can sense the bit line. So your interconnect latency is what dominates. So if you want to reduce the latency, you don't want that monolithic thing. You want to chop it up into pieces. There's another reason. If you have a single monolithic array, you can only access one location. You can, of course, put more ports, but that requires more ports essentially mean more of these bit lines and access transistors. You don't want that also because that becomes more expensive. So what people do is they reduce the latency of the memory access, enable multiple access in parallel. To be able to do that, you divide the monolithic array into multiple banks that can be accessed independently, or mostly independently, in the same cycle or in consecutive cycles. We're going to see examples of this. Each bank is smaller than the entire memory storage on the chip, and accesses to different banks can be overlapped. So you can start one access in one bank, and then you can start another access in the next bank in the next cycle. Now you can parallelize those accesses. And in existing DRAM chips, you have 16 banks, for example. SRAM on like an L3 cache or an L1 cache is also banked on a chip, so they can sustain multiple accesses concurrently. Okay, so an issue always in this case is how do you map data to different banks? This is also called how do you interleave data across banks? Like should you put an entire row of memory or entire physical page of memory in the same bank? Or should you put the first cache line in this bank, next cache line in the next bank, next cache line in the next bank, dot, dot, dot. So this is called the memory mapping or memory interleaving problem. And there's no perfect answer to this. This is actually a good problem to also look into, but it's a very complicated problem, I think, as we will see more when we get to it. But this is an example of memory bank organization. This is agnostic of the technology, as you can see, right? Technology sells maybe anything internally. It could be DRAM, it could be SRAM, it could be phase change memory. But essentially, most memory, it could be flash, most memory looks like this. You have a two-dimensional storage array called a bank, and you supply a row address and a column address. Essentially, you supply an address. The most significant bits indicate the row that you're accessing, and some of the least significant bits indicate the column within that row you're accessing. And then, basically, in this case, you supply the address. The most significant bits get decoded. Essentially, you activate this word line. All of the bits in the word line get to the column decoder, and the least significant bits determine which bits you select out. Okay, so there's a read access sequence that's essentially similar in many memories. You decode the row address and drive the word lines. Selected bits drive the bit lines. You read the entire row, and then you amplify the row data, which is not shown here. There's a sense amplification process over here. And then you need to decode the column address and select the subset of the row and send it to the output. And at the end of this, you pre-charge the bit lines for the next address. What does this mean? You prepare the array for the next access. In DRAM, it's called a pre-charge. It's also called pre-charge in SRAM. Essentially, you prepare the bit lines such that they go into a reference voltage so that you can sense the next activation. That's the idea. And this is true for all memory technologies, actually. Okay, let's talk about memory hierarchy. Some of these will be very familiar with for many of you. That's why we're going to go relatively fast in some of these. But essentially, we want everything from memory. We want both fast and large, but we cannot achieve both with a single level of memory. As a result, people have developed the idea of having multiple levels of storage that get progressively bigger and slower as the levels become farther away from the processor, and hopefully ensure most of the data the processor needs is kept in the faster levels. And this is the idea of the memory hierarchy. And this is my ugly picture of it. Essentially, you have a fundamental trade-off. Fast memory is small, large memory is slow. You have the idea of a memory hierarchy. You have the register file at the highest level of the memory hierarchy, if you will, or lowest, depending on how you think of it. And then the cache at the next level, and then some other cache at the next level, main memory, hard disk, tape, whatever you have over there, maybe. And clearly, there are trade-offs, right? Latency is lower over here, and it gets progressively higher as you go this way. Cost is higher over here because you want fast stuff to be here, fast memory to be here. Cost gets lower as you go to the right. Size becomes larger as you go to the right, and bandwidth becomes lower as you go to the right, essentially. So that's the trade-off that we're dealing with today. But we're also going to question this hierarchy. We built this hierarchy because you have good locality in the workloads, and you cannot do anything over here, any computation over here. Those are the assumptions under which this hierarchy was built. Right. Okay, so one of the assumptions is temporal locality. Basically, the idea over here is, I guess everyone knows about locality here, right? Okay, I'll go through this quickly because you must have seen it at some course. If not in computer architecture, probably in operating systems, right? Because virtual memory is also based on the locality principle. But basically, the idea is we want to store recently accessed data in fast memory. Fast memory could be automatically managed. It's called a cache if it's automatically managed. And the anticipation is that that data will be accessed again soon. This is the temporal locality principle, right? Recently accessed data will be again accessed in the near future. And this is what Maurice Wilks had in mind when he wrote this seminal paper on caches, essentially. This is in many ways regarded the first paper in caches. It's not true, actually. It's not the first paper that introduced a hardware cache, but it's perhaps the easiest to read and cleanest paper that introduced a hardware cache. It's a beautiful paper also. And I quote actually from him, basically, the use is discussed of a fast core memory of, say, 32,000 words as a slave to a slower core memory of, say, 1 million words in such a way that in practical case, the effective access time is nearer that of the fast memory than that of the slow memory. It's beautiful, right? It captures the concept nicely. Of course, it captures the mindset also, right? It's all about, as you go far away from the processor, these things are slaves. They're not doing any useful stuff, or maybe they're doing useful stuff, but they really are slaves to the processor. So it's a mindset that we may need to change also going into the future. Okay, the second principle that caching usually exploits is exploiting spatial locality. And this is basically, we want to store addresses adjacent to the recently accessed one in this fast memory, because we anticipate that addresses around the one that we access is going to be accessed soon again, accessed soon. Essentially, we logically divide memory into equal sized blocks, and we fetch to the cache the access block in its entirety. So even though we may access 8 bytes, we fetch 64 bytes. That is the cache block within which these 8 bytes reside. And the anticipation is that nearby data will be accessed soon. And again, this exists in many programs. Nearby data in memory will be accessed in the near future. That's the spatial locality principle. If you're doing sequential accesses in the instruction stream, whenever you're executing a program, it's usually sequential. That's what you get. If you're doing an array traversal, that's also true. If your data structures are laid out nicely, you will get sequential accesses. But it's not always true, actually. A lot of the graph programs today, as we will discuss, have a lot of random memory accesses. So this principle doesn't always hold. Temporal locality principle always doesn't hold also. It really is a program characteristic in the end. And this is actually not what Morris Wilks described. Morris Wilks didn't describe this principle. This principle was actually described in IBM 36085 for the first time. And IBM implemented a cache with 64-byte blocks at that time in 1968, as you can see. And we still have 64-byte blocks today. That's also good to think about this history. So we didn't change the memory hierarchy much. Even though we tried to improve a lot, we didn't change it much, fundamentally. Okay, so clearly these are fundamental principles that we built the memory hierarchies with. There's also another principle. Do you do manual or do you do automatic management? Manual means programmer manages the data movement across the levels. And it's usually too painful for programmers on substantial programs. Like virtual memory was developed to do so that the programmer doesn't do this management of data from the physical memory to physical disk, right? The memory gives the illusion that it's infinite capacity and it automatically manages the disk to physical memory movement. That's true for caches also, right? Caches could be managed by the programmer. It used to be managed by the programmer in the 1950s. It's still done in some embedded processors. There's an on-chip scratchpad. GPUs still have, they call it shared memory. Essentially, that's a scratchpad that's managed on the GPU. They also have caches, but they are parts that are manually managed. And if you know your program well, if you can design compilers really well, of course, manual management could be better than this automatic management, right? But it's still painful. The pain is still there. Automatic is hardware manages the data movement across levels transparently to the programmer. Hardware is just one example. Of course, software can also do this. But in a hardware cache, it makes sense for the hardware to manage it. So of course, programmer's life is easier. Simple heuristic is keeping most recently used items in cache. Of course, people have developed many, many heuristics over time. In fact, International Symposium on Computer Architecture, ISCA, the major conference in computer architecture, is sometimes jokingly called International Symposium on Cache Architecture, ISCA, because there are a lot of papers that appear on caches. It's still appearing, actually. It's good because it's such a fundamental thing, right? Okay, and the advantage is that the average programmer doesn't need to know about it. But of course, that's not the whole story, right? If you really need to optimize the performance of your program, you really need to know how big your cache is and what kind of policies it employs to optimize your performance. People have developed tiling methods, for example, to do matrix multiplication really fast. And that requires the programmer to actually either use a library that already does this or do it themselves. But for correct programs, you don't need it. That's the good part. You decouple the correctness from performance in this case. That's the nice fundamental trade-offs over here by enabling automatic management. Okay, so automatic management, this is the paper that I mentioned by Morris Wilks, and I already said this, but he essentially had automatic management in mind when he talked about caches at that time. He called them slave memories, right? By a slave memory, I mean one which automatically accumulates to itself words that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of main memory access to be incurred again. Again, it's beautiful wording, I think. It's very crisp. But as I said, this is not the first paper. The first paper in hardware caches is actually really this one. It's more or less a forgotten paper. Actually, I cannot find it online. Maybe I should put it on my website. This is a paper that talks about caching, but the caching at a different level. This is really operating system level caching. This is really hardware caching over here. And if you go back to that paper, I was prudent enough to copy-paste the cache structure that they have in that paper. And it looks very similar to the cache today, actually. So this is the data store of the cache. This is the associative address storage, which is a tag store. And they have some analog usage indicator. This is a reference bit for a cache block to do the replacement or not replacement, essentially. So it's very similar to today's cache structure. Essentially, not much has changed since 1962, as you can see, right? And this may not be the first paper. I'm not sure. It's always good to find the original source of some idea. In caching, this is the best I could get to. And I talked to a lot of people. IBM claims that they've done it earlier. They haven't been able to produce any paperwork that shows that. There are some claims also by Konrad Zuse's work here in Germany. But again, there's no work. But I don't know German also, so that's, that's the hard part. But maybe there's some work, but nobody has been able to produce something earlier than this one that convincingly showed that it's a hardware cache. Of course, software caches exist, right? And we knew that. OK, anyway, that's an aside. OK, so as a result, we have this memory hierarchy today, which this is one example of it. The manually managed part, at least in a general purpose processor, is limited to the register file today. And most of it is automatically managed, as you can see. And this part is managed by the system, hardware, software, cooperatively, by the virtual memory, the band paging system, clearly. Of course, there are parts of it where the programmer and compiler play a role with prefetch instructions in general purpose systems, but mostly they're automatically managed today. OK, let's go into the DRAM subsystem. Any questions so far? Is this all too basic? Interesting? Okay, at least it's interesting, I guess. OK. OK, so let's talk about the DRAM subsystem. This may not be something that you're as familiar with. I'm going to go through this bottom up, and then I'm going to go through this top down also to give you how this works. Essentially, it's a multi-dimensional structure. At the basis, you have cells, essentially. You have a two-dimensional array of cells, rows and columns, and you build banks on top of them, chips, ranks, DIMMs, and channels. Let's start with the two-dimensional array. Essentially, a two-dimensional array of cells is called a DRAM bank, rows and columns. We're going to start with that abstraction, and then we're going to break that abstraction later. A DRAM row is unfortunately called a DRAM page as well. This is where the virtual memory terminology gets overloaded. It has nothing to do with a virtual memory page. It's a hardware page. That's why I like calling it a row. And sense amplifier is also called a row buffer, and you'll see page buffer also. Each address that you get is a row-column pair, and access to a closed row, meaning that if the row is not open in the row buffer in the sense amplifiers, you need to activate that row first, which places the row into the row buffer. And then you can issue read and write commands, which gives you read and writes to the columns and the row buffer. And then once you're done with that row, with those accesses, you pre-charge the array. Essentially, you send a pre-charge command that closes the row and prepares the bank for the next access. We're going to go through an animation of this. Now, if a row is already open in the sense amplifiers, also called the row buffer, as I said, the access is much faster. Basically, you don't need the activate command because the row is already there in the sense amplifiers. You just need to read and write. And then when you're done with it, with the row, you can pre-charge it. This is my handwritten picture of a DRAM bank. We're going to look at it in more detail. But basically, in DRAM, this is the boundary of a DRAM chip, essentially. And you have multiple of these banks. But this is one example bank, and with some values that are associated. These are old values, but they're still reasonable. Essentially, you have 2 to the 14 rows and 2 to the 10 columns. And people try to make it rectangular so that they can maximize the number of bits and maximize the yield in a two-dimensional process. You basically, whenever you send the address from the DRAM controller, and you send the row address when you send an activate command, and row address gets slashed, and then you activate the row, which brings the data into the row buffer. And then once the activate command is done, you send the column address to read the column that you're looking for. So you send the addresses separately. Row address and column address come at different times. You could have done it earlier, but then it increased the chip pin count that you need. That's why you use the same address bus to multiplex row and column addresses. And that pin count is very important for cost. They want to minimize the pin count. And in DRAM chips, the data pins are also 8 bits. Essentially, you get 8 bits out of a single chip. It could be 16, more expensive. It could be 4, less expensive. 8 bits is the usual common case. And then you send the command also. So you have a command bus, address bus, and a data in or out bus over here. And a DRAM chip consists of multiple of these banks. And the banks share the command, address, and data buses. That's the beauty of, they want to minimize the number of pins. So the banks cannot be operated in parallel. They can be operated in a pipeline manner. So you send the row address and an activate command to bank 0. In the next cycle, you can send the row address and the activate commands to some other bank through the same channel, essentially. And they also share the data buses. So whenever one bank is transferring data, another bank cannot transfer the data. And the memory controller's job is to orchestrate all of that so that you don't have conflicts on the address buses, command buses, and the data buses. So it's basically very cheap. If you look at SRAM, it's a bit different because SRAM is on chip. Normally, you can access all of the banks in parallel at the same time because on-chip interconnects are much cheaper. You don't need to go through this off-chip interface, right? No pins needed for that. Okay, let's go through the DRAM bank operation in a little bit more detail. This is my pictorial view of it, columns and rows. Essentially, you have a row buffer. This is the sense amplifiers for a given bank. Each bank has a single row buffer because you need to have a sense amplifiers to sense the data. Initially, that row buffer is empty. Let's take a look at some access sequence. We want to access row 0, column 0 in this bank. The memory controller sends that address and row address 0 and an activate command to row address 0. Row decoder decodes it, activates the row, brings the data into the row buffer, and sense amplifiers amplify the data. Now, at some point, this becomes ready to read, and there's a timing parameter associated with it, activate to read delay. We're going to see these timing parameters more, and this is specified by the DRAM data sheets. If you're building a memory controller, you should read the data sheet and obey those timing parameters. And then you can send the read command with a column address. And that command essentially goes to the chip, and the chip multiplexes out the column 0 and sends it back to the memory controller. Okay, so this is a case when the row was not open. So you need to do activate and then read the data. Now let's take a look at the next access. Next access is to the same row, which is already in the row buffer, to a different column. Now the memory controller has information. It records the state of all of the banks. It knows that it just opened the row in this bank. So, and the next access is to the same row. So the memory controller doesn't need to open the row again. This is called a row buffer hit. Essentially, this is a very small cache over here. It could be 8 kilobytes or 2 kilobytes. So you get a hit, and you just need to send the column address and the read command. So this is much faster, as you can see, right? And then if the next access is to column 85 in the same row, the same situation. You get a hit, row buffer hit, and the memory controller just needs to send the column address. So row buffer hits are much faster than row buffer conflicts, as we will see in a bit. They take about 30% of the time, sometimes half, depending on the memory technology, of course, and the specifications that you have in the data sheets. So ideally, memory controllers exploit this row buffer locality, right? And there is some level of locality. This is far away from the caches, as you can see. It's a cache in front of the DRAM. It's a cache of the most recently activated row in a bank. Okay. Now let's say the processor wants to access row 1 and column 0. The memory controller figures out row 1 is not open in this bank. Some other row is open because it recorded it. It has data structures in hardware. And this is a row buffer conflict. And now the memory controller needs to, what it needs to do is prepare the array for access to another row, which means that pre-charge the array. It sends a pre-charge command, which clears the row buffer and sets the sense amplifiers to a reference voltage. And then the memory controller sends an activate to row address 1. And then the chip takes its time. And then after some point, row 1 gets amplified, appears over here. And after some delay is passed, the memory controller sends the column address. and the chip gives the column from that row. So clearly that row buffer conflict took a long time, right? And memory controllers optimize to try to maximize the row buffer hits, because you may actually have a lot of requests queued up in your memory controller queue. Which one do you service? Existing memory controllers mostly try to minimize the row buffer conflicts, maximize the row buffer hits. So even though there may be an older request to some other row, they may pick a younger request to a row that is already open. Now, you can think that this is a good thing because it tries to maximize the data bus bandwidth. But if these requests are from different applications, it's maybe a bad thing because now you're delaying some other application, right? And that's the essence of the memory performance attacks paper that we've done a while ago. And you can think about fixes to the problem. Okay, so DRAM chip, now I've introduced the banks. But the DRAM chip consists of multiple banks. 8 is a common number today. Actually, it's not true anymore. It's 16 in DDR4, for example. It depends on the technology again. But DDR4 has some other idiosyncrasies. But basically, you enable access to multiple banks in parallel. Banks share command and address and data buses, as I said. The chip itself is a narrow interface. Basically, you get 4 to 16 bits per read, not a lot. And of course, there's a lot of design decision. Changing the number of banks, size of the interface, pins, whether or not command, address, data buses are shared has significant impact on the DRAM system cost, which we're not going to go into. This is one example. It's an old chip. I think it's a Micron chip, actually. It's nice because it shows a lot of the circuitry. And I base my numbers on this. For example, you have 2 to the 14 rows. You have 2 to the 10 columns. And you can see the different banks here nicely. Different banks have different row address decoders, as you can see. So they can be independently accessed. But they share this logic over here, as you can see. So you could actually send a command in a given cycle only in a single bank. And you do across different banks in multiple cycles. And you can see there's other stuff going on, sense amplifiers, and then a column decoder. There's other stuff here that you don't need to know about. Bank control logic. There's a refresh logic, as you can see. There's a refresh counter that enables the thing to refresh itself once in a while. That is also dictated by a command by the memory controller. Memory controller says refresh, and it waits for some time. And that's a handshake. Not a handshake, but that's specified by the DRAM standard. It's synchronous. You basically send the refresh command. You're supposed to wait for some time before sending any command to the DRAM chip. That's why it consumes a lot of time, actually, and power. OK, and then over here, there's a lot of mess. There's a lot of analog circuitry to ensure that the data is transferred correctly. You don't need to know about that clearly. But here, there are some interesting things. Even though this is an 8-bit chip, you see that you're reading 32 bits of data, actually. So they're actually doing a lot of internal prefetching of the data into this read latch. And modern DRAM has what is called burst mode. The first read, you can get out quickly. You need to wait for some time. That's the first 8 bits. But if you're reading consecutive 8 bits, you can get the consecutive 8 bits very quickly because of this internal prefetching. So you actually read 32 bits. They give you only 8 bits in a cycle, but you can get the next 8 bits very fast, next 8 bits really fast. This is called burst length. So modern DRAM can give you essentially a single cache line worth of data within a burst. Or I should say 64 bits of data. That's not a cache line. We're going to do something else to get the entire cache line, actually, as we will see in the next slide. So this is 8 bits. Actually, this gives you only 32 bits. But a lot of modern DRAM gives you 64 bits. This is a bit old. OK, now we're going to introduce something that widens the interface. So the interface here is only 8 bits. OK, in consecutive cycles, you get 32 bits. But what if you want to get much higher? This is the idea of a DRAM rank. Essentially, you put multiple chips on a single module so that you can form a wide interface. I'm going to show you a picture of this. But basically, all chips comprising a rank are controlled at the same time. They respond to a single command. And they share address and command buses, but provide different data across different data buses. Essentially, this is like a rank of soldiers. You have a rank of chips that are put together. The commander gives the command. That's the memory controller. And the soldiers respond with the same data, hopefully. And a DRAM module consists of 1 or more ranks. For example, a DIMM, dual inline memory module. That's what you plug into your motherboard if you're doing that. So for example, if you have a chip with an 8-bit interface, if you want to read 8 bytes in a single access, you use 8 chips in a DIMM. And this is a picture of it, basically. This may be familiar. You have 8 chips over here. They share the command buses, address buses. Those are the 2 things over here. And the data buses are separate, as you can see. So you basically get 64 bits of data in a given cycle. And if you have burst mode over 8 cycles, you get 64 times 8 bits, which is 64 bytes, a single cache line. That's the idea. So clearly, a DIMM is nice over here. The reason it's done this way is this keeps the chip cost low, because you don't need to add more pins. You just need to add another module that has this sort of interface. And these are cheaper than the pins. OK, so this is my picture from the paper that tried to solve the fairness in memory access scheduling problem a long time ago. I still like this picture. It's also another XFIG picture, by the way. Thanks. OK, so the advantages of a DIMM is it acts like a high-capacity DRAM chip with a wide interface. So we're improving here, as you can see, both capacity and the width, bandwidth, essentially. And it also gives some flexibility to the memory controller. Memory controller doesn't need to deal with individual chips now. It can get a lot of data from all of the chips at the same time. But of course, there's a disadvantage, which is granularity. Now your accesses cannot be smaller than the interface width. Right? You're doing 64-bit access, and if you want to utilize byte burst mode, you have to get 64 bytes. But if you need only 8 bytes, you cannot do it, right? Because you created your system so that it's optimized for the 64-byte access. So this is a problem. I think going forward, actually, figuring out the solution to this granularity problem is going to be important. And people have shown that you're wasting a lot of power whenever you're doing random access to 8 bytes, for example. You're really bringing, you really need 8 bytes, but you're fetching 64 bytes. So by definition, you're wasting 87.5% of your memory bandwidth. Right? OK. So if you want to increase the capacity, things become more messy. Essentially, you need to connect more DIMMs. This is a messy picture, unfortunately, but this is one way of connecting more DIMMs to a single channel. Essentially, somehow you interconnect the DIMMs, and this enables even higher capacity. But depending on how you interconnect the DIMMs, interconnect complexity can be high, and energy consumption can be high, because these are actually long traces in a printed circuit board, essentially. Right? That's a lot of communication. This is where 3D stacking can be useful. If you can stack a lot of memory on top of each other, these interconnects become much shorter. Of course, the question is how do you design those interconnects becomes it's a research problem today, actually. But this is how you get more capacity in a single DRAM chip, with a single DRAM channel. OK. Of course, scalability is limited by this now, your interconnect complexity. That's why interconnects are very important. How do you interconnect them is important. You can do a mesh topology like this. I don't know if it works really well. One thing that didn't work for a company like Intel, for example, Intel was pushing fully buffered DIMM. Does anybody know fully buffered DIMM? OK, you don't look that old. OK, I'm just kidding. Maybe you read a lot. But fully buffered DIMM was a DIMM standard that Intel was pushing in the early 2000s, maybe even earlier than that. But basically, what they wanted is a very high capacity memory in a single channel. And it looked like this, except the interconnect was a bit weird. A bit weird meaning that it was a daisy chain. Does anybody know what a daisy chain is? OK, the daisy chain is basically you have a controller. It's connected to the first DIMM. And that DIMM is connected to the next DIMM. That DIMM is connected to the next DIMM, next DIMM, next DIMM, next DIMM, next DIMM. That's the only interconnection that you have. So to be able to access memory that's over here, you need to go through the first DIMM, second DIMM, third DIMM, fourth DIMM, dot, dot, dot. And I believe they were proposing 8 DIMMs. So if you wanted to access memory that's far away over here, you need to go through 8 hops. So now you have completely asymmetric latencies in memory. So your performance depended very heavily on where your data is. And also, there was some other problem with the fully buffered DIMM. To be able to do that interconnect, somehow they had these advanced memory buffer chips inside the DIMMs that enabled them to route the messages to the destination. And that consumed a lot of power. I believe there was some implementation issue over there, but still, it adds power consumption also. So that thing didn't take off. So even big companies cannot push for ideas that are not that great, I guess, in this case. Or maybe the idea was not done well at that time. So it's a good question. So I don't believe the daisy chain was a good answer. Daisy chain was the fundamental problem, I think, with that particular design. If they had some other interconnect, that could have worked, but then, of course, there's a downside to that interconnect. So the reason they pushed daisy chain was it was easier to adopt, right? But it wasn't adopted clearly because of that daisy chain. Okay, so DRAM channels. So you can also, this is a single DRAM channel. You can also have multiple DRAM channels. This is my picture. Basically, you have multiple DRAM controllers. That's the idea. You have two different DRAM controllers, essentially two different pins, two different sets of pins for address, command, and data buses. Clearly, this increases the number of pins in the processor, right? So in this case, you have two independent channels. That's the common case. But you can also have two dependent channels to increase your bandwidth. That way, it looks like a single memory controller that's connected to two different DRAM channels. Each of the channels provides 64 bits per cycle. And now you can have a wider interface that way and still high memory capacity. But you cannot independently control those channels. That's the trade-off. And this is our generalized memory structure. Essentially, you can have two memory channels over here. Each memory channel can have multiple DIMMs. Each DIMM can have multiple ranks. And in each rank, you have multiple chips. In each chip, you have multiple banks, as you can see over here. Each bank consists of this two-dimensional area of cells, and that's the cache line. I think this is overall a five-dimensional structure if you go through all of these dimensions. And this is another picture of it. And I actually give you some references over here, which we may or may not cover. This is a subarray level parallelism paper that I mentioned earlier that Samsung and Intel evaluated independently and showed that they wanted that idea. And this is decoupled direct memory access. This is actually a paper that talks a lot about internals of a DRAM. Maybe we'll cover it. We don't know. I don't know yet. But this is another picture of the DRAM structure. Okay, and I recommend some readings. These are not yet required. But basically, if you really want to learn about the DRAM organization operation basics, unfortunately, in my opinion, there is no good material. If you want to read the data sheets, you will not get the insights out of them. These are, again, the benefit per word that you would get out of these sections will be very high compared to the data sheets that you may need to discover on your own. These are some of the first works that we've done when we first started looking into DRAM in a lot more depth. Basically, these sections 1 and 2 of these papers, they actually describe what's happening internally in DRAM and why these timing parameters exist, for example. And if you want to learn more about refresh, this paper talks about refresh a lot. Any questions? I feel like I'm talking a lot. Okay, maybe. So let me give you the top-down view. We've gone bottom-up, built up to that 5-dimensional hierarchy. Let's do the top-down view. I'm going to start from the channel. I'm going to start with a real example. Basically, this is some Intel processor. It doesn't need to be Intel. Every system looks like this today. Basically, you have multiple memory channels, and each channel may have multiple DIMMs, as you can see in this picture. If you look at a DIMM, it has a front and back, and it has multiple ranks. Front can have a rank, and back can have some other rank. There's some serial presence detect circuitry that has some non-volatile memory inside it so that you can remember some information, like what kind of DIMM it is, what kind of parameters does it support. Memory controller basically queries this and figures out what to do with this memory whenever you plug this in. And a rank is a collection of 8 chips in this case. If each of them has an 8-bit interface, you get 64 bits out of it. Sometimes you actually have a 9th chip over here, and that means that you have error correcting codes. One of the chips is dedicated to ECC, such a waste, actually, a lot of waste of memory, because not all of that memory is used for ECC. But yeah, that's how it is. And that's a different ECC than what we talked about in DRAM ECC. It's not, this is out of DRAM ECC. You use a separate chip. Memory controller really implements the ECC algorithm. Now today, in these chips, we're having ECC also. Okay, that was a side. Okay, if you look at a rank, this is rank 0, rank 1. Ranks channel the address and command buses, and also they share the data bus, but they multiplex. Basically, you cannot access 2 ranks in parallel. You need to switch between the ranks. Ranks are there just to improve capacity of a DRAM chip mainly. If you actually map your data badly such that you need to access this rank first, and then this rank, and then you basically keep flip-flopping between two ranks, your performance becomes terrible because the rank switching penalty exists, actually. There's a rank switching penalty because it takes time to go from, switch the buses from one rank to another rank. And this is specified in the DRAM data sheets. Okay, so let's look at a rank internally. Now we're going top-down. So you have a chip select signal that selects the rank based on the address that the memory controller provides. So if you break down a rank provides a 64-bit interface, but the chips don't have that interface, so you need to put multiple chips together, and each chip provides 8 bits of those 64 bits, and that's how they get connected to the data bus of the rank. But each chip has 8 pins here, 8 data pins. Okay, if you go inside a chip has 8 banks, as we've seen, in this case 8. But these 8 banks each can provide 8 bits of data in a cycle, but they get multiplexed. So only one bank can provide the data in a given cycle, and then you need to multiplex them. But you can overlap the activation latencies clearly across the banks. Right? Okay, and if you break down a bank, we're back to the two-dimensional array. It's columns and rows. And this is one example. Basically, you have 1-byte columns. You have a 2 kilobyte row. It's a 2 kilobyte row in this particular bank. But remember, the entire row size is really dictated by this, right? You have 2 kilobytes, so it's really 16 kilobyte row that you have. Whenever you open a row, you're really opening 16 kilobytes. 2 kilobyte in each chip. Okay? Okay, and then we don't want to go into the cell. Basically, the rest is cells. Okay, so that's the top-down view. So let's take a look at an example of transferring a cache block. So this is our physical memory space, and we have a 64-byte cache block. And this needs to somehow get mapped to a channel. So in this case, we map it to rank 0, dim 0, channel 0, for example. Of course, there's a mapping mechanism that exists in the memory controller, and operating system has some influence of it, but not perfect influence on it. This is one of the hairy issues. How does your data get mapped from virtual memory to physical memory and physical memory inside the DRAM structure? There's not a lot of software control over this today. And actually, a lot of the mapping is controlled by the memory controller, but internally there's mapping that's controlled by the memory chip itself also. And those mappings are not really exposed to the software. So software may not be able to do perfect mapping of data. Okay, so basically assume that your cache block is mapped over here. Essentially, we're going to read that cache block. How are we going to read that cache block? We can only read 64 bits. The first 64 bits of the cache block get mapped here. You basically activate those rows in all of these chips, and you bring down, you read 8 bits from each chip. That gives you the first 8 bytes, 64 bits of the cache block. You get the 8 bytes, and then the next 8 bytes come from the next column in the same row in different chips. You get that. And then you do the next one, next one, next one. Basically, consecutive columns give you the consecutive bytes in the cache block. So a 64-byte cache block in this case takes 8 bus cycles, I/O cycles to transfer. And during the process, 8 columns are read sequentially, as we can see. So it's a cumbersome process, basically, to get 64 bytes out of memory. So that leads to also latency, basically. So there are latency components in basic DRAM operation. There's a CPU to controller transfer time. CPU asks the memory controller, I want this data. So that takes some time on chip latency. I'm even ignoring the caches right now, right? So you need to go through the caches to check the caches where the data exists there. If it doesn't exist, you go to the controller. And there's some latency in the controller. You need to wait for your turn, if you will. There's queuing and scheduling delay. And then the access is converted to basic commands. And then there's transfer time between the controller and DRAM. Controller asks the DRAM to activate and then read. And then there's the DRAM bank latency. These are fancy other names that you may see. Column access strobe is essentially a read command. Row address strobe is an activate command. So basically, if the row is open, you send a read. If the row is not open, but the array is already pre-charged, you send an activate plus a read. And the worst case, the memory controller needs to pre-charge the array, send an activate, and then send a read command, basically. This is also, of course, a read. Write command is also another CAS command. And then there's the transfer time from the DRAM to the controller. There's also bus latency on top of these latencies. And then there's a transfer time from the controller to the CPU. So it's a huge round trip, actually. It takes a lot of time. For example, Xbox 360, a memory access, if you need to go to the main memory, it took about 650 cycles. That was a very long transfer time. It's not as bad in many processors, but it could be bad. OK, so we want multiple banks, as we said, so that we could actually enable multiple access in parallel. Bits in the address determine which bank an address resides in. And multiple independent channels serve the same purpose, but actually they're even better because they have separate data buses in channels. They give you increased bus bandwidth. And enabling more concurrency requires reducing the bank conflicts and channel conflicts, and people spend a lot of time to try to reduce these conflicts clearly. Because if you have bank conflicts, and if you want to get both of the data at the same time, you're serializing your requests, right? That's true for channels also. So that's why address mapping becomes important. So how do you select and randomize bank channel indices in an address? Usually, the memory controller uses lower order bits to map to different banks and channels. They have more entropy. They change more frequently, of course, across accesses. Or they use randomizing hash function. They XOR different parts of the address bit so that you have a randomized function. Hopefully, the hope is that different accesses will go to different banks. Right? Of course, you can run into bad situations where you keep getting bank conflicts. For example, if you have only 16 banks, let's say, and if your consecutive cache blocks are in consecutive banks, and if your stride is 16, you always get the same bank, right? You don't take advantage of the bank level parallelism clearly, because you always access cache blocks 0, 16, 32. They all map to the same bank. That's why memory controllers try to randomize. But again, those randomizing functions are selected based on some hardware designer's judgment, right? And they're not exposed to the software usually. So there's a huge mapping problem as a result. Maybe software can do a much better job of mapping if these functions were better, right? If more information was provided from the DRAM system, how does the DRAM system look to the software? Software could map the data much better. But that interface doesn't exist today. You don't. And people reverse engineer actually this. People reverse engineer where different addresses go to, which banks different addresses go to. But they very much depend on the memory controller. So you could do that. But it's not a nice thing, right? It's better to have a better interface such that the software is told, OK, this is where your data will go if you select these addresses this way. And then now the software can optimize. I think this is one of the places where there's a lot more work that needs to be done between the operating system, compiler, and hardware interface. OK, so how multiple banks help? Hopefully this is obvious. But basically, if you have a single bank, the address goes to that bank. This is the first access. You wait for DRAM access, and the data comes. And before the data comes, you can send the next address to the same bank, because you know that the data will come at some point, and you waited for enough delay before you send the next activate. So this is the activate to activate delay, or read to read delay, depending on whether thing is open or not. This is at a higher level abstraction. Essentially, you wait for DRAM access to do 3 accesses. Accesses are serialized, right? But if you have different banks and your addresses go to different banks, now you can start the accesses in a pipeline manner. You send the first access to bank 0, next access to bank 1. So the accesses to DRAM banks are overlapped, as you can see. And the data comes in consecutive cycles over here. So that's the beauty of having multiple banks. Of course, if you have bank conflicts, you're back to the square one. Even though you may have 4 banks, your access timeline may look like that. That's why minimizing the bank conflicts is really important, actually. Of course, you can have multiple channels. In multiple channels, you have separate address and data buses, so you can send address 0 and address 1 concurrently on the different data buses, assuming you don't have channel conflicts, assuming the addresses go to different channels, essentially. So minimizing channel conflicts is also important. So this is one example. If you have a single channel system with 8-byte memory bus with some assumptions, essentially, I'm not going to go through this in detail, but there are 2 types of major interleaving mechanisms. Consecutive rows of memory are in consecutive banks. this is what happens over here. Access to consecutive cache blocks can be serviced in a pipeline manner in this case. Or you could do a cache block interleaving. You interleave consecutive cache blocks in consecutive banks. So in this case, access to consecutive cache blocks can be serviced in parallel over here. Anyway, we don't need to go through this in detail, but it becomes more complicated as we will see in a little bit. But these are the two major interleaving. Usually people use this one actually. Basically what they do is they cache block 0 in the physical address space goes to channel 0. Cache block 1 goes to channel 1. Cache block 2 goes to channel 2. Cache block 3 goes to channel 4. And cache block 4 goes to bank 1 in channel 0. So they interleave across channels, and they interleave across banks as well. So consecutive cache blocks, they try to minimize the possibility of channel conflicts first and then bank conflicts next. That's the idea. Of course, this assumes a streaming access pattern, right? You're accessing consecutive cache blocks concurrently. That may not be the case, right? It's not assuming a random access pattern. Okay, a lot of the DRAM controllers actually do some sort of randomization also. And basically, they take and XOR some of the bits in the address and form the bank index. Of course, it's a reversible randomizing function. Essentially, hopefully you get more randomization. And if you want to know more about randomization to reduce bank conflicts, this is a beautiful paper that was written by Bob Rao in ISCA 1991. It's a very theoretical paper that talks about Galois fields and how to actually design memory banks to minimize bank conflicts. And the reason they designed, actually, this was related to Cray processors. They wanted to design, because you have a lot of memory accesses, you want to minimize the bank conflicts in a supercomputer. And they wanted to pseudo-randomly interleave the accesses. And of course, this proposes a lot of fancy schemes, but they're not employed in existing systems because they're a bit more complicated than a simple XOR function. Okay. So this problem becomes even more hairy if you have multiple channels. Essentially, if you go back over here, this doesn't have any channel bits, right? This basically, if this is a 31-bit address, I think, let's see, 14, 17, yes, 31-bit address. And row bits come from here, bank bits come from here, column bits, byte and bus come from here, and then we randomize the bit. But we didn't even talk about channels. Where do you put the channel bit? Essentially, usually people do cache block interleaving, but your consecutive cache blocks is in different places depending on where you put the channel bit clearly. Again, this is something you can have fun with. This problem becomes pretty complex, essentially, if you want to optimize for bank conflicts. One thing that I will talk about briefly is there's interaction with virtual to physical mapping. Basically, operating system can influence where an address mapped to in DRAM. Why? Because whenever you go through the virtual memory system, you translate a virtual address to a physical address. And that's under the control of the operating system, right? Operating system assigns a virtual page number, a physical frame number to a virtual page number, right? Whenever it's doing the page replacement. Page offset remains the same, of course. So if you look at the physical address, depending on where the bits are selected, so bank bits, for example, may come from this part of the physical frame number, right? And if that's the case, the operating system can influence which bank or the memory allocator can influence which bank a particular page goes to, right? And if it's intelligent, it can try to separate different pages to different banks, especially if those pages are conflicting with each other for some reason in terms of the access sequence, right? So that's the idea over here. But of course, it may not have full influence. If the bank bits are selected from here, well, too bad, right? The operating system has no control in terms of where it can place the data because it gets to play with only this part, virtual page to physical frame number translation. If the channel bit is, for example, selected here, which is true in current systems, most current systems, a lot of current systems are actually configurable. You can set a register saying, I want this mapping to be row interleaving or cache line interleaving. But if it's cache line interleaving, a cache line is smaller than a page. As a result, you select the channel bit from here, and operating system basically has no control. Clearly, this may not be a good thing, right? If you want to map your data. For example, if you want to do computation inside a memory channel, and if you want to operate on different cache blocks at the same time, if your memory mapping is this way, well, you're not going to go far because your cache blocks are in different memory channels. So you need to change the mindset to actually do the data mapping differently also. This is one example of reviewer comments that I will give you an example of. Reviewer comment says, okay, you need to change the mapping to be able to do computation in a memory channel. Yeah, right. You do need to change the mapping, yes. So that's actually something that's really important to realize. And the realization, I think, is this. The fundamental realization is this mapping is there because of the paradigm that we have today, which is the processor-centric paradigm, right? The processor is the one that needs the data. That's why we've designed some mapping mechanisms. These also are not perfect, in my opinion, but these are designed with some mindset in mind. If the mindset is something different, if the paradigm is something different, you cannot assume that this mapping should stay constant. You have to change this mapping with that mindset in mind. And you really cannot penalize some other paradigm because it has to change that mapping, because that paradigm requires that some other mapping that you never considered because your thinking was different, right? This is something that I would like you to think about, because whenever you change some part of the system, some other parts of the system that were designed with some other thinking need to change as well. And I think that's really important. Okay, so going back, operating system can today influence which bank channel rank a virtual page is mapped to, but not always, again. So it can perform page coloring, for example. Page coloring is a mechanism where operating system can color the pages and allocate different colors to different banks, for example, to minimize bank conflicts, to minimize interference between different applications. So for example, it can map different applications to different channels or to different banks. And this is one paper, early paper that we had done in the area. Or it can actually minimize the latency in the network by doing the data mapping nicely. And that's another paper that maybe I have a reference to. Okay, this is one of the papers. This is one of the early papers where we proposed essentially application-aware memory channel partitioning so that applications that interfere badly with each other are mapped to different channels by the operating system. This requires some hardware support, but very little hardware support. And it also looks into the interaction between partitioning of the channels across applications plus the memory scheduling. What should the memory scheduler do? What should the operating system do? And it's funny that when we first submitted this paper to ASPLOS, Architectural Support for Programming Language and Operating Systems, it was rejected from there. It was saying, basically, the reviewer said that there was too much hardware in it. When we submitted to Micro, it got in, it got accepted. But one of the comments we got was, this has nothing to do with Micro, there's too much operating system in it. It's a combination of both, actually. I thought ASPLOS was a better fit for this paper, Architectural Support for Programming Languages and Operating Systems, actually. That's what essentially this paper is about, but anyway. So if you get rejected, don't worry. If you have a good idea, push for it. Okay, and this is the other paper that I mentioned, basically. This proposes some application-to-core mapping policies to minimize the interference that you get in the network. This is very sophisticated. A lot of heuristics employed here. This is much simpler, actually, in terms of the design. But if you want to consider the network and the memory controller's locations, so if you have a mesh network, for example, and if you have memory controllers in different locations, and you want to minimize the interference of the applications while maximizing system performance, you need to consider the location where you map an application, which core do you place an application, and also the interactions of that core with different applications that are placed close by. So this actually proposed a few principles on how to do that. Okay, a bit more on reducing bank conflicts. I lied to you, meaning that I said bank is the lowest level of abstraction. It is true from the memory controller's point of view. When you look at a memory controller's point of view, it sees the bank and thinks that there is only a single row buffer. But if you go internally inside the DRAM chip, that's not the case. Basically, a bank actually has a lot of rows, 32,000 rows in this case, and people try to increase it so that it can increase the capacity. If you put the row buffer over here, this is a lot of interconnect. The latency will be too long. So what internally manufacturers do is they divide the bank into much smaller sub-banks or sub-arrays, each of them 512 rows, and the sense amplifiers are actually associated with each sub-array. So you have 512 rows or 1K rows and sense amplifiers, the row buffer. And you have 64 of them in this case. So whenever you activate a row, what happens is you really place the data, sense the data in this local row buffer. Because the interconnect latency is low, you can keep the memory latency low. Yes, memory latencies are not improving, but those interconnect latencies are actually very long. If you actually built this one, the memory latency would be much longer. So internally, the chip looks like this. And to drive the data out of this local row buffer, that muxing happens over here, and you have a global row buffer. This is actually a misleading picture. Sorry about that. This global row buffer gets you maybe 16 bits. This is about 2,000 bits. This is about 16 bits. So the interconnects that you need to get 16 bits out of here to almost to the periphery of the chip is very large. So you drive very large interconnects. That's why you cannot put 2,000 of them like this. That's why the chip has this structure. Now, we realized that this structure, well, we knew about the structure, but we realized that you could exploit this structure with very small changes to the DRAM chip such that you reduce the bank conflicts. And the idea in this paper over here is to exploit the subarray level parallelism. Expose to the memory controller these subarrays and enable, with very simple changes to the chip, the activation of these subarrays concurrently. So today, you can activate only a single row in the entire bank. With very small changes, if you have a latch over here, another latch over here, you activate a row in the subarray. It gets stored over here. And then if you want to activate some other row in some other subarray, that's essentially a bank conflict today. Here, you can do that, because that goes to some other subarray. You activate that subarray, that gets latched over here. You just need to be able to switch between these two different subarrays whenever you need to access those different rows. And that's the idea. This increases the power consumption in the DRAM chip a little bit because you need to keep multiple local row buffers active, not just one in this case. And you had some additional circuitry. But according to the results that we have, it reduces the bank conflicts greatly. Because you have, assuming even if you have only 8 of these potentially active at the same time, essentially, if 2 requests were going to the same bank before, they would serialize. But if they're going to the different subarrays in the same bank, now they can be serviced mostly in parallel. Not perfectly in parallel, but mostly in parallel. And that was the idea that Samsung and Intel also independently validated in the paper that I mentioned, the 4-page paper. And they said that this is good for scaling the latencies because we don't need to wait for, we can increase the write latencies this way to ease the circuit level issues that we're having, but we can tolerate those latencies, write latencies, because we can exploit these subarrays. And if you want to know more about that, that's the paper. Okay, let me talk about refresh also, and then we'll be done. Oh, what time are we supposed to end today? You mean right now? Okay. Should we talk about refresh, or should we leave it for tomorrow? Depends on how long. I'll keep it short. How about that? Okay, let me keep it short, because we're going to talk more about refresh tomorrow, actually, more detail. Okay, so refresh is also fundamental. Basically, a DRAM capacitor charge leaks over time, and the memory controller needs to periodically refresh to restore each charge. So fundamentally, you need to activate and pre-charge every row every n milliseconds. Typical n today is 64 milliseconds. Actually, this is reducing already. In LPDDR chips, we're already at 32 milliseconds. At high temperatures, you need to actually make it 16 milliseconds today. In the past, it was 32 milliseconds. But it's going to go down, basically. You need to refresh more often. So there are clearly implications on performance here. DRAM bank is unavailable while refresh. Today, you can do per bank refresh. If you really want to go into the detail, I'll recommend some papers. We're not going to go into that much detail. It used to be that DRAM chip, the entire DRAM rank is unavailable during refresh because you didn't have the per bank refresh command. Now, manufacturers added the per bank refresh command, so only the DRAM bank is unavailable. Other banks can be accessed. But even that's not enough, actually. We have a proposal where you could parallelize the refreshes to the access to the same bank. Again, the idea is building on the subarray level parallelism. Whenever one subarray is being refreshed, another subarray can be accessed. I think that subarray level granularity exposed to the memory controller is a really good thing. And of course, this leads to long pause times. If you actually refresh all rows in a burst every 64 milliseconds, the DRAM will be unavailable until refresh ends. It used to be the case. The memory controller used to do this, but quickly they figured out that distributed refresh is much better. Basically, all rows are refreshed immediately after one another. That's burst refresh. Today, each row is refreshed at a different time at regular intervals. So it's like this. Today, the memory controller sends a refresh command every some number of microseconds. And the memory itself refreshes the rows when it receives the refresh commands. So the interface is a bit weird today. The memory controller doesn't know which rows are being refreshed. Internally, the chip knows which rows are being refreshed. The memory controller's function is to send the commands at regular intervals. That's it. Tell the chip to refresh itself. So the control of when to do the refreshes in the memory controller. If the memory controller forgets a refresh, you may lose data, of course. But it's the responsibility of the chip to figure out what to refresh internally. This ensures that the control is in the memory controller, but the memory controller doesn't need to deal with what to refresh internally. That's what the compromise is. Of course, you can always refresh a row by sending an activate and a pre-charge again, right? That's essentially replenishing the charge in the row. Okay, so in the past, it used to be this bad picture. As you could see, you refreshed all of the rows at the same time, and clearly that leads to a very long pause time if you needed to access DRAM at this point in time. Okay, distributed refresh eliminates long pause times. How else can we reduce the effect of refresh on performance? Basically, if we can reduce the number of refreshes, that would be great. Right? And that's what this paper proposes. So there are many downsides of DRAM refresh. Each refresh consumes energy. It leads to performance degradation, as we've discussed. It leads to quality of service impact. It leads to pause times. It may not be long, but it's still a pause time. And refresh rate limits actually DRAM density scaling. And if you want to know more about this, we're going to cover this paper tomorrow. And this paper actually proposes a very nice way of reducing the refreshes a lot. But the way it's proposed in this paper is not implementable. So it actually opened up a lot of research on figuring out how to make it implementable. And I'm going to talk about that tomorrow because it's not going to be easy. The idea at the surface is very beautiful, very simple, and very implementable in the memory controller perspective. But really how to do it is the hairy part. And this enabled us to build the infrastructure that I showed you, the FPGA-based memory testing infrastructure, because our goal was to actually implement what we proposed over here. But we didn't know how to implement it without understanding the memory chips. Oh, you have a class here?
Yeah.
Okay, I'll be done.
Oh.
Okay. Okay, thank you very much. Okay, well, I guess we have a hard constraint here right now. Quality of service constraint. But this is a good time to stop. Let me give you the idea very quickly, basically. The idea very quickly is based on this. This is the next paper that we did in the area, based on our infrastructure that we built because we wanted to realize this work. Basically, the data retention time profile of DRAM looks like this. Today, we're refreshing everything every 64 milliseconds. But most of the cells can retain data much longer than that. So it's very heterogeneous. So the idea is to have a heterogeneous refresh rate scheme. And if you actually figure out which cells can retain data for a long time, you can reduce the refreshes by 75% almost if the distribution looks like this, right? Most of the cells can retain data for longer than 256 milliseconds. So you set your refresh rate for those cells for 256 milliseconds, for everything else 64 milliseconds. So that gets rid of almost 75% of your refreshes. But of course, the difficulty is this. That's the idea proposed in the paper. The difficulty is this is dependent on the location of the cell. This is dependent on the value pattern that is stored in the cell and the cells around it. And the retention times also depend on time, the quantum-like effects that I said that happen randomly. So how do you actually make that idea work given all of this is the tough part. Of course, there's a lot of other work on parallelizing refresh to the accesses, which I'm not going to cover. And this is a really good time to stop, I think. OK, so I guess we'll need to let them in. I'll see you tomorrow. What time is it tomorrow? 10 a.m. OK. It's a bit early, but I'm sure I will see you. Okay. Oh, it's normally at 10:15, right here? More or less, OK. OK, yeah, I mean, I'm fine. Whatever you prefer. Do you prefer 10:15 or 10? Well, I guess let's do 10:15 because some people may assume that it's 10:15. OK?